Welcome to Astro Odyssey. Explore the universe. Imagine standing in your backyard on a clear night, looking up at the constellations that have guided humanity for millennia. Among the thousands of glittering points of light, there is one system that holds a special place in the human imagination. Alpha Centauri. To the naked eye, it appears as a single, brilliant star, the third brightest in the night sky. But this is a cosmic illusion that masks a complex and violent reality. Alpha Centauri is not just a star. It is a triple star system, a gravitational dance involving three distinct suns. While most of us are used to the solitary existence of our own sun, the majority of stars in the Milky Way actually exist in pairs or groups. Alpha Centauri is our nearest example of this multipolar stellar arrangement, located a staggering 4.37 light-years away from Earth. To understand the distance we are talking about, we have to move beyond miles and kilometers, which become useless at this scale. A light-year is nearly 6 trillion miles, 6 multiplied 10 raised to power 12 miles. If the sun were the size of a ping-pong ball in New York City, Alpha Centauri would be another ping-pong ball, located in Los Angeles. The vast emptiness between us is the primary barrier to our status as an interstellar species. Within this system, we find Alpha Centauri A and Alpha Centauri B. These two stars are the twins of the system, orbiting a common center of mass every 80 years. Alpha Centauri A is a G-type main sequence star, very similar to our sun in color and temperature, while B is slightly smaller and cooler. Together, they provide a sense of familiarity, sun-like environment, where we might hope to find a home. However, there is a third member of the family that changed everything we thought we knew about the neighborhood. Proxima Centauri, discovered much later than its brighter siblings. Proxima is a small, dim red dwarf. It is the true closest star to us, sitting at about 4.24 light-years away. It orbits the A and B pair at a massive distance, taking hundreds of thousands of years to complete a single loop. For decades, Proxima Centauri was ignored as a dim bulb in the cosmic hallway. Red dwarfs are the most common stars in the galaxy, but they are notorious for being small, cool, and incredibly volatile. Yet, in August 2016, the European Southern Observatory made an announcement that shook the scientific world. They had found a planet orbiting this tiny star. This planet was named Proxima Centauri B. Its discovery was a watershed moment for astrobiology. We weren't looking at a gas giant like Jupiter or a frozen wasteland like Neptune. We were looking at a rocky world, roughly the same size as Earth. The proximity of this discovery felt almost like a cosmic invitation. The very nearest star to our own has a planet that could, in theory, support life. The excitement surrounding Proxima B stems from its location in the Goldilocks zone or the habitable zone. This is the region around a star where the temperature is just right for liquid water to exist on a planet's surface. On Earth, water is the fundamental solvent for life. Find water, and you find the possibility of biology. However, the Goldilocks zone around a red dwarf like Proxima is vastly different from the one around our sun. Because Proxima is so cool and dim, its habitable zone is pulled inward, tight against the star. Proxima B orbits so close that the time it takes to complete one revolution is only 11.2 Earth days. This extreme proximity creates a gravitational phenomenon known as tidal locking. Just as the moon always shows the same face to the Earth, Proxima B is believed to always show the same face to its star. This means one side of the planet is locked in perpetual, blistering daylight, while the other side is shrouded in an eternal frozen night. This creates a planet of extremes. The day side is baked by constant radiation, potentially creating a desert landscape where the sun never sets. The night side is a dark wilderness, where temperatures could drop low enough to freeze the very atmosphere into a layer of nitrogen ice. The transition between these two, the twilight zone, is where the real mystery lies. Astronomers refer to this transition as the Terminator Line. It is a ring of perpetual sunset that circles the planet. In this thin sliver of geography, temperatures might be moderate. Here, the heat from the day side and the cold from the night side could mix, potentially allowing for liquid water. and a climate that isn't entirely hostile to life. But the habitability of Proxima b isn't just about temperature, it's about the star itself. Unlike our stable, middle-aged sun, red dwarfs are flare stars. They are prone to sudden, violent outbursts of energy that can double the star's brightness in minutes. These flares drench orbiting planets in X-rays, an ultraviolet radiation that would be lethal to unprotected organisms. This brings us to the central tension of our exploration. Proxima b is the closest exoplanet we will ever find. It is a world we could potentially reach with robotic probes within a human lifetime. It sits in a zone where water can exist, but it is also a world under constant bombardment from its own sun, orbiting in a gravitational grip that prevents it from spinning. To understand if life exists there, we have to look at the history of the planet. Did it form where it is now, or did it migrate from further out? If it formed far from the star and moved inward, it might have brought huge amounts of ice and water with it, potentially becoming a water world, with deep global oceans that could shield life from radiation. If it formed in its current position, it might be a dry, airless rock, its atmosphere long since stripped away by billions of years of solar flares. The stakes for this research are incredibly high. If we find life on the very first planet we check outside our solar system, it implies that the universe is teeming with biological activity. As we look at the Alpha Centauri system, we are also looking at the future of human exploration. Projects like Breakthrough Starshot are already designing light sails that could travel at 20% the speed of light. Such a craft could reach Proxima b in just over 20 years, sending back the first close-up photos of an alien world. Imagine the first image we receive from Proxima b, a horizon of red-tinted mountains under a massive, unmoving red sun. Perhaps there are oceans reflecting the light of Alpha Centauri A and B in the distance. The visual of three suns in one sky isn't just science fiction. It is the physical reality of our closest neighbors. This video will dive deep into the data we have gathered from our greatest telescopes and the models built by our most brilliant physicists. We will examine the magnetic fields, the atmospheric chemistry, and the eyeball Earth theories that suggest how a tidally locked world might actually function. We are living in the first generation of humans who don't have to wonder if there are planets around other stars. We know they are there. Now, the question is anyone home? Join us as we cross the interstellar void to explore the strange, beautiful, and terrifying reality of life on Proxima b. To understand the dilemma of Proxima b, we must first understand the nature of its parent star. Proxima Centauri is an M-type red dwarf, the most common class of star in the Milky Way. While our sun is a roaring yellow furnace of middle-aged stability, red dwarfs are the small, thrifty survivors of the cosmos. They burn their hydrogen fuel so slowly that they can live for trillions of years, long after our sun has expanded into a red giant and collapsed into a white dwarf. This longevity is the first pro in the habitability column. Evolution on Earth took nearly 4 billion years to produce complex life. Because red dwarfs live so long, life around them has an almost infinite window of time to emerge, adapt, and evolve. However, this biological head start comes at a devastating price. The temperament of the star itself. Because Proxima Centauri is small, roughly 12% the mass of our sun, its core is under less pressure, which is why it burns cooler. But this low mass also means the star is fully convective. In our sun, energy moves through radiation in the inner layers and convection in the outer layers. In Proxima, the plasma is constantly churning from the core all the way to the surface. Like a boiling pot of water, this constant churning creates incredibly powerful and tangled magnetic fields. When these magnetic fields snap and reconnect, they release superflares. In 2017, astronomers observed a flare from Proxima that made the star 1,000 times brighter in a matter of seconds. For a planet like Proxima b, which sits incredibly close to its star, these flares are not just spectacular light shows, they are existential threats. On Earth, we are protected from solar flares by a thick atmosphere and a powerful magnetic field. But Proxima b is 20 times closer to its star than Earth is to the sun. At that range, a superflare doesn't just hit the planet, it engulfs it. These events saturate the planet in high-energy X-rays and ultraviolet radiation, which can shatter organic molecules and potentially sterilize the surface. This leads us to the problem of the close inhabitability zone. Because the star is so dim, the region where liquid water can exist is pushed inward. Proxima b is only 4.6 million miles away from its star, a tiny fraction of the 93 million miles between Earth and the Sun. This proximity makes the planet a victim of intense tidal heating, where the star's gravity literally stretches and squeezes the planet's core. Gravitational kneading can lead to extreme volcanic activity. While volcanoes can help create an atmosphere throughout, too much volcanism can lead to a runaway greenhouse effect, turning the planet into a twin of Venus, a pressure cooker of sulfuric acid and carbon dioxide, where life, as we know it, is impossible. Then there is the issue of tidal locking, which we touched on earlier. When a planet orbits this close, the star's gravity creates a tidal bulge in the planet's crust. Over millions of years, this bulge acts like a brake, slowing the planet's rotation until it matches its orbital period. Proxima b likely has a permanent day side and a permanent night side, a concept that challenges everything we know about climate. On a rotating planet like Earth, the Coriolis effect helps distribute heat and drives the weather patterns that keep our planet habitable. On a tidally locked world, the atmospheric circulation is entirely different. Heat must be transported from the day side to the night side via massive, planet-wide wind systems. If the atmosphere is too thin, the heat won't move fast enough, and the air on the night side will literally freeze and fall to the ground as snow. This is known as atmospheric collapse. If the gases on the night side freeze into solid ice, the atmospheric pressure drops, drawing more air from the day side to the night side to be frozen. Eventually, the entire atmosphere could end up trapped in a giant glacier on the dark side of the planet, leaving the day side a vacuum-sealed wasteland. However, some climate models offer a more optimistic deep dive into this dilemma. If Proxima b has a thick enough atmosphere, perhaps dominated by CO2 or nitrogen, the winds could be efficient enough to keep the night side from freezing. This would create a global climate that is bizarre but potentially stable, with a permanent hurricane-like storm sitting directly under the unmoving sun. The red dwarf dilemma also extends to the light itself. Our plants evolved to use the visible light of the sun for photosynthesis. Proxima Centauri emits mostly infrared light. If plants or their alien equivalents exist on Proxima b, they wouldn't be green. To absorb the lower energy photons of a red dwarf, they might be black or dark purple, designed to soak up every bit of energy available. This infrared-heavy environment also means the planet would be visually dark to human eyes. Even at high noon on the day side, the brightness might feel like a gloomy twilight on Earth. The star would appear much larger in the sky, about 3 times the size of our sun, but it would be a deep, angry crimson, casting long, unmoving shadows across the landscape. There is also the XUV evolution problem. During its youth, the first billion years, a red dwarf is even more active than it is in its middle age. Proxima Centauri likely spent its first few 100 million years blasting Proxima b with radiation. If the planet didn't start with a massive water budget or a very thick shield, it might have been dried out before life even had a chance to begin. Scientists are currently debating whether a magnetosphere could save the planet. If Proxima b has a molten iron core and is spinning even slowly due to tidal locking, it might generate a magnetic shield. This shield would act as a deflector for the stellar wind, potentially preserving the atmosphere despite the star's constant tantrums. Another layer of the dilemma is the stellar wind. Proxima Centauri loses mass through a stream of charged particles that is much denser than our own solar wind. This wind exerts a pressure on the planet's upper atmosphere, effectively sandblasting the gases away into space. To survive, Proxima b needs to be tough, either very massive or very magnetically active. We must also consider the ocean circulation on such a world. If Proxima b is a water world, the ocean currents would be the primary heat transporters. These currents would move warm water from the substellar point, the spot directly under the sun, to the dark side. This could create a liquid ocean even in the permanent darkness. shielded by a layer of surface ice. That brings us to the eyeball Earth hypothesis. Imagine a planet that is mostly frozen, a giant white snowball, except for a circular patch of open water, and land directly facing the star. From space, the planet would look like a giant eye staring into the cosmos. This pupil of the eye would be the only habitable place in the system. The final part of the dilemma is chemical. In our system, the sun's UV radiation helps create ozone O3, which protects us. But the specific spectrum of a red dwarf might not create the same chemical reactions. Without an ozone layer, even a thick atmosphere might not be enough to protect the surface from the hard radiation of a stellar flare. In conclusion, the dilemma of Proxima b is a battle between time and violence. The star gives the planet trillions of years to foster life, but it also subjects it to a level of radiation and gravitational stress that our Earth has never had to endure. Is Proxima b a resilient super-Earth, or is it a warning of how difficult life truly is to sustain? The most critical question for any planet's habitability isn't where is it, but rather can it keep its air. For Proxima b, this is a life or death struggle against its own sun. An atmosphere is more than just a gas to breathe. It is a thermal blanket and a radiation shield. Without it, liquid water boils away into the vacuum of space, and the surface is scorched by the unfiltered fury of the star dot. To understand how a star steals an atmosphere, we have to look at high-energy photons. Proxima Centauri emits a disproportionate amount of X-rays and extreme ultraviolet XUV radiation. These photons are so energetic that when they hit the upper layers of an atmosphere, they don't just heat the gas, they ionize it, stripping electrons away from atoms and turning the air into a charged plasma. Once ionized, these atmospheric particles are no longer bound by the simple rules of gravity. They become susceptible to the stellar wind, a relentless stream of protons and electrons flowing out from the star at hundreds of kilometers per second. This wind acts like a cosmic sandblaster, physically pushing the ionized gas away from the planet and out into the interstellar void. For Earth, our primary defense is our planet's molten iron core generates a magnetic field that acts like a protective bubble, deflecting the solar wind around us. Proxima b, however, is much closer to its star. To survive, it would need a magnetic field significantly stronger than Earth's to withstand the much higher dynamic pressure of Proxima's stellar wind. Scientists use a concept called hydrodynamic escape to model this, because Proxima b is so close to its star. Its upper atmosphere is perpetually heated to thousands of degrees. This heat causes the atmosphere to puff up and expand. If the gas expands beyond the hellsphere, the region where the planet's gravity is dominant, it simply spills out into space and is lost forever. This process is exacerbated by stellar flares. While the steady stellar wind is bad, a superflare is a catastrophe. During a flare, the X-ray flux can increase by a factor of 100 or more. This flash heating can cause the atmosphere to expand so rapidly that it creates a planetary wind, where the atmosphere essentially blows itself off the planet in a massive, temporary burst. We have seen this happen in our own solar system. Mars was once a warm, wet world with a thick atmosphere and flowing rivers, but because Mars is small and lost its global magnetic field early on, the sun's solar wind slowly stripped its atmosphere away over billions of years. Proxima b faces a version of this Marsification that is orders of magnitude more intense. There is also the photo dissociation problem. When high-energy UV light hits water vapor H2O in the upper atmosphere, it breaks the molecules apart into hydrogen and oxygen. Hydrogen, being the lightest element, is the easiest for the stellar wind to carry away. This water loss is permanent. Once the hydrogen is gone, the oxygen stays behind, potentially creating a false positive oxygen atmosphere that contains no life. If Proxima b lost its water this way, during its first billion years, it might today be a desiccated world, a bone-dry rock with a surface of oxidized minerals, essentially a hyper-radiated version of the Sahara Desert. This early loss is the biggest hurdle for models that suggest Proxima b could be Earth-like today. However, there is a counter-theory. Volcanic out. If Proxima b has a restless, molten interior, perhaps kept hot by the tidal kneading, we discussed earlier, it might be constantly refilling its atmosphere. Volcanoes can pump massive amounts of carbon dioxide, nitrogen, and water vapor back into the sky, potentially replacing what the star steals. This creates an atmospheric tug-of-war. On one side, the star is stripping gas away. On the other, the planet's interior is replenishing it. The fate of life on Proxima B depends entirely on which side is winning. If the outgassing is too strong, you get a Venus-like nightmare. If it's too weak, you get a Mars-like vacuum. Another factor is impact delivery. In the early days of the system, comets and icy asteroids from the outer reaches of the Alpha Centauri system could have bombarded Proxima B. These dirty snowballs could have acted as a cosmic refueling service, dumping trillions of tons of water and gases onto the planet even as the star was trying to strip them away. We also have to consider the composition of the atmosphere. A heavy atmosphere, one rich in carbon dioxide, CO2, or even heavier noble gases, is much harder for a star to strip than a light atmosphere of hydrogen and helium. If Proxima B managed to hold on to its heavier gases, it might still have enough surface pressure to support liquid water. There is a fascinating possibility called the ion cage effect. Some researchers suggest that if a planet is tidally locked, the magnetic field might trap ions in a specific way that prevents them from escaping the dark side. This could lead to an atmosphere that is thin on the day side, but relatively thick and stable on the night side. To settle this debate, astronomers are waiting for the James Webb Space Telescope, JWST, and the Future LOVOIR mission. These telescopes are designed to perform transmission spectroscopy, measuring the starlight as it passes through the planet's atmosphere during a transit. This would reveal the chemical fingerprint of the gases present. Unfortunately, Proxima B does not transit its star from our perspective. It doesn't pass directly in front of it. This means we have to use phase curve analysis, looking at the tiny variations in the system's total light as the planet shows us its day side and night side. If there is no atmosphere, the temperature difference between the sides will be extreme. If there is an atmosphere, the heat will be more evenly spread. We see that the existence of an atmosphere on Proxima B is the ultimate filter for life. Without it, the planet is just a dead rock. But if it had survived the star stealing of the last 4 billion years, it means Proxima B is far more resilient than we ever imagined and potentially a perfect cradle for an entirely different kind of biology. After discussing the violent flares and atmospheric stripping, it's easy to view Proxima B as a lost cause. But in science, hostile is a relative term. On Earth, we have found life in the boiling vents of the deep ocean, inside solid rock, miles underground, and even in the cooling water of nuclear reactors. The case for hope for Proxima B rests on the idea that life doesn't need a perfect world. It just needs a foothold. The first pillar of hope is the shielding power of water. If Proxima B is a water world, with global oceans hundreds of kilometers deep, the surface radiation becomes irrelevant to anything living in the depths. Just 10 meters of water can block most lethal UV and X-ray radiation. In this scenario, a thriving biosphere could exist in the dark, pressurized silence of an alien ocean, completely indifferent to the tantrums of the star above. These subsurface oceans might be powered by hydrothermal activity, just as life on Earth's ocean floor thrives on chemical energy rather than sunlight. Organisms on Proxima B could cluster around volcanic vents. On a tidally locked world, the constant gravitational squeezing from the star would ensure the planet's core remains hot and active, providing a steady supply of nutrients for billions of years, optimized to soak up every red and infrared photon, creating a landscape that looks like a charcoal sketch, but is teeming with biological activity. Hope also comes from the magnetic dynamo theory. While Proxima B is likely slow rotating, it isn't stationary. A rotation period of 11 days is still fast enough to generate a magnetic field if the interior is molten. Recent simulations suggest that even a modest magnetic field could be enough to create safe zones where the atmosphere is protected from the most direct hits of the stellar wind. We must also look at slow evolution, because Proxima Centauri will live for trillions of years. Life there isn't in a rush. On Earth, life had to survive the sun's increasing brightness. On Proxima b, the star's luminosity is incredibly stable over vast times. This stellar patience might allow for incredibly complex symbiotic relationships to develop, creating an ecosystem that is more interconnected than anything on Earth. The panspermia possibility adds another layer of hope. Alpha Centauri, A and B, are sun-like stars. If life evolved there first, it's possible that impact ejector rocks blasted off a planet by a meteor could have traveled between the stars over millions of years, seeding Proxima b with hardy microbes that had already learned how to survive in the system. Even the flare cycles might be a benefit. Some biologists argue that regular, non-lethal doses of radiation can actually accelerate the rate of mutation and evolution. The harshness of Proxima Centauri might be the very thing that forced life on Proxima b to become more adaptable, smarter, and more resilient than life on a boring, stable planet like Earth. There is also the deep crustal biosphere. Even if the surface is a radiation-baked desert, the interior could be full of liquid-filled pores and caves. On Earth, the deep biosphere may account for a huge percentage of our planet's total biomass. Proxima b could be a hollow world of life, hidden beneath a kilometer of protective rock. We should not underestimate the atmospheric chemistry of a red dwarf planet. If the atmosphere is rich in nitrogen and methane, it could create a haze similar to Titan's. This organic haze is incredibly good at blocking UV radiation while letting heat through, acting as a global pair of sunglasses for the planet. The oceanic heat transport model suggests that a global ocean would be incredibly efficient at moving heat. On a tightly locked world, the ocean wouldn't just sit there. It would form massive, predictable currents that pump warm water to the ice-covered dark side, potentially melting leads or openings in the ice, where sea life could breathe and interact with the atmosphere. Finally, there is the human element. The fact that we are already dreaming of ways to visit this world, using lasers and light sails, means that Proxima b is no longer just a dot in a telescope. It has become a goal. If life isn't there yet, the case for hope might eventually be used bringing the seeds of Earth to the nearest star. We see that the obstacles to life on Proxima b are immense, but they are not insurmountable. The universe has a way of surprising us. From the eyeball Earth to the neon glow of fluorescent reefs, Proxima b represents the ultimate what-if. In our search for a second home, we are currently standing on the threshold of a new era in astronomy. For decades, Proxima b was just a wobble in a data setter, mathematical certainty, but a visual ghost. As we move through 2026, that is beginning to change. We are transitioning from the discovery phase to the characterization phase, where we stop asking if these worlds exist and start asking what they are actually made of. The first major player in this shift is the James Webb Space Telescope, JW. While JWST has already provided groundbreaking data on Alpha Centauri A, its mid-infrared instrument, MIRI, is being pushed to its absolute limits to detect the heat signatures of planets in our neighboring system. In fact, recent observations in late 2025 and early 2026 have hinted at a possible gas giant orbiting Alpha Centauri A, proving that the system still has many secrets to reveal. However, the true holy grail for Proxima b lies with the extremely large telescope, currently under construction in the Chilean desert, with a primary mirror 39 meters across. It will be the largest optical telescope on Earth. Once it sees first light later this decade, it won't just detect Proxima b, it may actually be able to directly image the planet. For the first time, we could see a dot of light that isn't a star, but a world. The ELT's high-resolution spectrographs are designed to do something that was once considered impossible: sniff the atmosphere of Proxima b for biosignatures. By analyzing the light reflected off the planet, scientists can look for the chemical fingerprints of oxygen, methane, and carbon dioxide. If these gases are found in the right proportions, it would be the smoking gun for biological activity. Beyond the ELT, NASA is already planning the Habitable Worlds Observatory, HWO. This super Hubble is being specifically engineered to identify Earth-like planets around Sun-like stars, while Proxima b orbits a red dwarf. The HWO will use advanced coronagraphs to block out the blinding light of Alpha Centauri A and B, searching for Earth 2.0 hidden in their habitable zones. But telescopes can only tell us so much. To truly understand Alpha Centauri, we must go there. This is the vision of Breakthrough. Although the project faces immense engineering and geopolitical hurdles, such as the need for a multi-kilometer laser array, remains our most scientifically grounded hope for interstellar travel. The goal is to send a fleet of starships that could reach the system in just over 20 years. Imagine the year 2050. The first starship arrives at Proxima Centauri. It streaks past Proxima, be at 20% the speed of light, snapping high-resolution photos that reveal the geography of the planet. For years later, those images arrive on Earth. For the first time, we would see the coastlines, the mountains, or perhaps the dark purple forests of another world. This mission would be the ultimate Apollo moment for the 21st century. It would prove that humanity is no longer confined to a single solar system. But even before we send probes, missions like Ptolemy, a small, dedicated space telescope, working to map the gravitational environment of Alpha Centauri to ensure our future probes know exactly where to aim. We must also consider the philosophical impact of finding life next door. If Proxima B is inhabited, it means the universe is a crowded place. It would change our religions, our politics, and our understanding of our own importance. We would no longer be the only observers of the cosmos. We would be part of a larger, galactic community. If, on the other hand, we find that Proxima B is a barren, radiation-blasted rock, it doesn't mean our journey was a failure. It makes our own Earth seem even more precious, a rare, fragile oasis in a vast and often hostile desert. It would reinforce the idea that habitability is a delicate balance, one that we must protect on our own home world. The study of Alpha Centauri is also a lesson in long-term thinking. Interstellar travel requires a commitment that spans generations. The scientists who design these missions today may not be alive to see the data return. It is a testament to human curiosity that we are willing to start journeys that we know we cannot finish. There is also the potential for technicism. While we focus on finding microbes in plants, the Breakthrough Listen project is scanning the Centauri system for radio or laser signals. If an advanced civilization exists there, they would likely be aware of us, too. After all, from their perspective, our sun is just another bright star in their night sky. As we look toward the 2030s and 2040s, the space race is becoming an interstellar race. National space agencies and private foundations are collaborating more than ever because the challenges of reaching another star, too great for any one nation to handle alone. Alpha Centauri is the common goal that could unite humanity in a singular purpose. We are also developing new forms of propulsion beyond light sails. Concepts like pellet beam propulsion or nuclear thermal rockets could eventually allow for larger crewed missions to the Centauri system. While these are still in the realm of theory, the rapid pace of technological growth in the 2020s suggests that the impossible is moving closer every day. Ultimately, Proxima B is a mirror. In it, we see our fears of a dying planet, our hopes for a new beginning, and our unquenchable thirst for discovery. It is the closest shore on the other side of the cosmic ocean, and we have already begun to build the ships that will take us there. The video ends, not with an answer, but with an invitation. The stars are no longer just lights in the sky. They are destinations. Whether Proxima B is a thriving world or a silent rock, it has already succeeded in doing one thing. It has made us look up and wonder what if. So, as we wait for the first light of the ELT and the first launch of the starships, we remain a species of explorers, forever reaching for the next horizon. Alpha Centauri is waiting, and the journey has only just begun.